Welcome. This is our first module in Material Science and Engineering, the nature of materials. In this section, I will be giving some example of the changes in the way materials are used. Each of these examples spanning about 100 years, which is not more than a single lifetime. This, for example, the kettle, which is one of the oldest of the household appliances and the one found in more homes than any other. There is even evidence of a 4,000-year-old kettle. Early kettles heated directly over a fire were of necessity made of materials that could conduct heat well and withstand exposure to an open flame. Examples of these materials are cast iron, bronze, and now we have polypropylene. Here, for example, we have another one. The earliest vacuum cleaners were human-powered. The materials were by today's standards very primitive. The cleaner was made of almost entirely from natural materials. The only metal parts were the straps that linked the bellows and the can containing the filter. The electric vacuum cleaner first appeared around 1908, and by the 1950, the design had evolved into the cylinder cleaner. The developments since then have been rapid, driven by the innovative use of new materials. Early cameras were made of wood and constructed with the care and finish of a cabinet maker. Wood, canvas, and leather were quickly replaced by precision-engineered steel bodies and control mechanisms. Then from the 1960s on, by aluminum, magnesium, or titanium for low weight, durability, and prestige. Digital technology fractionated the market further. High-end cameras now have optical systems with compound lenses, combining glasses with tailored refractive indices, manufactured with the precision and electronic sophistication of scientific instruments. At the other end of the range, point-and-shoot cameras with molded polypropylene or ABS bodies and acrylic or polycarbonate lenses fill a need. Finally, we have planes. Early planes were made of low-density woods, steel wire, and silk. Wood remained the principal structural material of airframes well into the 20th century, but as planes got larger, it became less and less practical. The aluminum airframe exemplified by the Douglas DC-3 was the answer. It provided the high bending stiffness and strength at low weight necessary for scale-up and extended range. Aluminum remained the dominant structural material of civil airliners for the remainder of the 20th century. By the end of the century, the pressure for greater fuel economy and lower carbon emissions have reached a level that made composites an increasingly attractive choice, despite their higher cost and greater technical challenge. The future of airframe is exemplified by 787 Dreamliner of Boeing, which is 80% carbon fiber reinforced plastic by volume, claimed to be 30% lighter per seat than competing aircraft. Each of these examples gave us an idea how materials have evolved and at the same time how it feels the need of an ever-changing world. By the end of this lesson, you should be able to analyze the evolution of engineering materials in the different time periods and describe the engineering materials needed in the 21st century. Cite the four components that are involved in the design, production, and utilization of materials, and briefly describe the interrelationships between these components. Cite three criteria that are important in the material selection process. Enumerate and describe the different classification of traditional and advanced engineering materials, and explain the composition of engineering materials as well as the chemical bonding involved in the formation of engineering materials. This will be the outline of my presentation. Let's start first with the historical perspective. Materials are probably more deep-seated in our culture than most of us realize. Transportation, housing, clothing, communication, recreation, and food production, virtually every segment of our everyday lives is influenced to one degree or another by materials. Historically, the development and advancement of societies have been intimately tied to the members' ability to produce and manipulate materials to fill their needs. In fact, early civilizations have been designated by the level of their materials development. We have the Stone Age, Bronze Age, and the Iron Age. Throughout history, materials have had limited design. The ages of man are named for the materials he used. We have the stone, the bronze, iron, among others. And when a man died, the materials he treasured were buried with him. For example, Tutankhamun in his enameled sarcophagus, Agamemnon with his bronze sword and mask of gold, Viking chieftains in their burial ships, each treasure representing the high technology of their day. In this chart, we can see the evolution of engineering materials all the way back from 10,000 BC until 2020. The materials of prehistory were ceramics and glasses, natural polymers and composites. Weapons, always the peak of technology, were made of wood and flint, buildings and bridges of stone and wood. The development of rudimentary thermochemistry allowed the extraction of first copper and bronze, then iron, stimulating enormous advances in the technology. Cast iron technology established the dominance of steel in engineering since the evolution of steels. Light alloys and special alloys has consolidated their position. By the 1950s, engineering materials meant metals. Engineers were given courses in metallurgy. Other materials were barely mentioned. The Industrial Revolution transformed economies that has been based on agriculture and handicrafts into economies based on large-scale industry, mechanized manufacturing, and the factory system. New machines, new power sources, and new ways of organizing work made existing industries more productive and efficient. Industrial revolution is a consequence of material development. The development of many technologies that make our existence so comfortable has been intimately associated with the accessibility of suitable materials. An advancement in the understanding of a material type is often the forerunner to the stepwise progression of technology. For example, automobiles would not have been possible without the availability of inexpensive steel or some other comparable substitute. In our contemporary era, sophisticated electronic devices rely on computers that are made from what we call semiconducting materials. Now that we know the historical perspective of materials, we are now ready to differentiate material science from materials engineering. Sometimes it is useful to subdivide the discipline of material science and engineering into material science and engineering subdisciplines. Strictly speaking, material science involves investigating the relationship that exists between the structures and the properties of materials. In contrast, materials engineering is on the basis of this structure-property correlation, designing or engineering the structure of a material to produce a predetermined set of properties. From a functional perspective, the role of a material scientist is to develop or synthesize new materials, whereas materials engineer is called upon to create new products or systems using existing materials and or to develop new techniques for processing materials. In this chart, we can see the four components of the discipline of material science and engineering and their interrelationship. The structure of a material usually refers to the arrangement of its internal components. Structures can be divided further into the subatomic structure, which involves electrons with the individual atoms and interactions with their nuclei. On an atomic level, structure encompasses the organization of atoms or molecules relative to one another. The next larger structural realm, which contains large groups of atoms that are normally agglomerated together, is termed microscopic, meaning that is which is subject to direct observation using some type of microscope. Finally, the structural elements that may be viewed with the naked eye are termed macroscopic. While in service, use of materials are exposed to external stimuli that evoke some type of response. For example, a specimen subjected to forces will experience deformation, or a polished metal surface will reflect light. A property is a material's trait in terms of the kind and magnitude of response to a specific imposed stimulus. Generally, the definition of a properties are made independent of the material shape and size. Virtually, all important properties of solid materials may be grouped into 6 different categories. We have mechanical, electrical, thermal, magnetic, optical, and the deteriorative properties. In addition to structure and properties, two other components that are involved in the science and engineering of materials are the processing and performance. With regard to the relationship of these four components, the structure of the material will depend on how it is being processed. Furthermore, a material's performance will be a function of its properties. So looking back again in this interrelationship between processing, structure, properties, and performance, here we can see the relationship between material science and materials engineering. Now that we know the difference between material science and materials engineering and the interrelationship between them, now we are ready to discuss why study material science and engineering. A familiar item that is fabricated from 3 different material types is the beverage container. Beverages are marketed in aluminum, which is a metal, cans, glass, which is a ceramic, bottles, and plastic, which are polymers, or even bottles. The material used for this application must satisfy the following constraints. First, it must provide a barrier to the passage of carbon dioxide, which is under pressure in the container. Second, it should be non-toxic and reactive with the beverage and preferably be recyclable. Third, it should be relatively strong and capable of surviving a drop from a height of several feet when containing the beverage. It should be inexpensive and the cost to fabricate the final shape should be relatively low. If optically transparent, it should retain its optical clarity, and it should be capable of being produced having different colors and are able to be adorned with decorative labels. As you can see, the basis for the decision how to select the kind of materials in order to satisfy all of these needs, for example, should depend on your knowledge of the properties of materials. So why do we study materials? Many an applied scientist or engineer, whether mechanical, civil, chemical, or electrical, will be at one point or another be exposed to a design problem involving materials. Examples might include a transmission gear, the superstructure for a building, an oil refinery component, or an integrated circuit chip. Of course, material scientists and engineers are specialists who are totally involved in the investigation and design of materials. Many times, a materials problem is one of the selecting the right materials from many thousands that are available. There are several criteria on which the final decision is normally based. First of all, the in-service condition must be characterized, for this will dictate the properties required of the material. On only rare occasion does a material possess the maximum or ideal combination of properties. Thus, it may be necessary to trade off one characteristic for another. The classic example involves strength and ductility. Normally, a material having a high strength will have only a limited ductility. In such cases, a reasonable compromise between two or more properties may be necessary. A second selection consideration is any deterioration of the material properties that may occur during service operation. For example, significant reductions in mechanical strength may result from exposure to elevated temperature or corrosive environment. Finally, probably the overriding consideration is that of economics. What will be the finished product cost? A material may be found that has the ideal set of properties but is prohibitively expensive. Here again, some compromise is inevitable. The cost of a finished piece is also includes any expense incurred during fabrication to produce the desired shape. The more familiar an engineer or scientist is with the various characteristics and structure, property relationships, as well as the processing techniques of materials, the more proficient and confident he or she will be to make the judicious materials choices based on these criteria. Now that we know the reason why we study material science and engineering, we are now ready to classify the materials. It is conventional to classify the materials of engineering into six broad families. We can see here in the figure the menu of engineering materials. We have metals, polymers, elastomers, ceramics, glasses, hybrids, which are also known as composites. The members of a family have certain features in common. They have similar properties, similar processing routes, and often similar application. The first one is, or the metals. Metals are stiff. They have relatively high elastic moduli. Most, when pure, are soft and easily deformed. They can be made strong by alloying and by mechanical and heat treatment, but they remain ductile, allowing them to be formed by deformation process. Certain high-strength alloys have ductilities as low as 1%, but even this is not enough to ensure that the material yields before it fractures, and that fracture, when it occurs, is of a tough, ductile type. Partly because of their ductilities, metals are prey to fatigue, and of all the classes of materials, they are least resistant to corrosion. The next to our family of engineering material is the ceramics. Ceramics have high moduli, but unlike metal, they are brittle. Their strength in tension means the brittle fracture strength. In compression, it is the brittle crushing strength, which is about 15 times greater. And because ceramics have no ductility, they have they have low tolerance for stress concentrations or for high impact stresses. Ductile materials accommodate stress concentrations by deforming in a way that redistributes the load more evenly, and because of this, they can be used under static loads within a small margin of their yield strength. However, ceramics cannot do that. Brittle materials always have wide scatter in their strength, and the strength itself depends on the volume of material under load and the time over which it is applied. So ceramics are not as easy to design with as metals. Despite this, they have attractive features like they are stiff, they are hard, and abrasion resistant. Hence, they're used for bearings and cutting tools. They retain their strength to high temperatures, and they resist corrosion well. The next one are the glasses. Glasses are non-crystalline or amorphous solids. The most common are the soda lime and borosilicate glasses, familiar as bottles and ovenware, but there are even many more. Metals too can be made non-crystalline by cooling them sufficiently quickly. The lack of crystal structure suppresses plasticity, so like ceramic, glasses are hard, brittle, and vulnerable to stress concentrations. Polymers. Polymers are at the other end of the spectrum. They have moduli that are low, roughly 50 times lower than those of metals, but they can be strong, even nearly as strong as metals. A consequence of this is that elastic deflections of polymers are large. They creep at even at room temperature, meaning that a polymer component under load may, with time, acquire a permanent set. And their properties depend on temperature, so that polymer that is tough and flexible at 20 degrees Celsius may be brittle at 4 degrees Celsius, for example. Some polymers are mainly crystalline, some are amorphous, some are a mix of crystalline and amorphous. Transparency goes with the amorphous structure. If these aspects are allowed for in the design, the advantage of polymers can be exploited, and there are many. When combinations of properties such as strength per unit weight are important, polymers can compete with metals. They are easy to shape. Complicated parts of performing several functions can be molded from a polymer in a single operation. The large elastic deflections allow the design of polymer components that snap together, making assembly fast and cheap. By accurately sizing the mold and pre-coloring the polymer, no finishing operations are needed. Polymers resist corrosions and have low coefficient of frictions. Good designers exploit these properties of polymers. Elastomers are long-chain polymers above their glass transition temperatures. Their Young's modulus is 105 times less than that of a typical metals. They have enormous elastic extension. Hybrids are combinations of two or more materials in a predetermined configuration and scale. They combine the attractive properties of other families of materials while avoiding some of their drawbacks. The family of hybrids includes fiber and particular components, sandwich structures, lattice structures, foams, cables, and laminates. Almost all the materials of nature like wood, bone, and skin and leaf are hybrids. Fiber-reinforced composites are of course the most familiar of the hybrids. Now that we learned the different families or classification of materials, we are now ready to discuss the advanced materials. Materials that are utilized in high technology applications are sometimes termed advanced materials. By high technology, we mean a device or product that operates or functions using relatively intricate and sophisticated principles. Examples include electronic equipment, computers, fiber optic systems, spacecraft, aircraft, and military rocketry. Those advanced materials are typically traditional materials whose properties have been enhanced, and also newly developed high-performance materials. Furthermore, they may be of all material types like metals, ceramics, polymers, and are normally expensive. Advanced materials include semiconductors, biomaterials, and what we term materials of the future, that is, the smart materials and nano-engineered materials. The properties and applications of a number of these advanced materials, for example, the materials that are used for lasers, integrated circuits, magnetic information storage, liquid crystal displays, and other optics, are also discussed in the next slide. Semiconductors have electrical properties that are intermediate between electrical conductors like metals and metal alloys, and insulators like ceramics and polymers. Furthermore, the electrical characteristics of these materials are extremely sensitive to the presence of minute concentrations of impurity atoms, for which the concentrations may be controlled over very small spatial regions. Semiconductors have made possible the advent of integrated circuitry that has totally revolutionized the electronics and computer industries, not to mention our lives over the span of 3 decades. Biomaterials, on the other hand, are employed in components implanted into the human body for replacement of diseased or damaged body parts. These materials must not produce toxic substances and must be compatible with body tissues. Example, it must not cause adverse biological reactions. All of the above materials, metals, ceramics, polymers, composites, semiconductors, may be used as biomaterials. For example, some of the biomaterials that are utilized in artificial hip replacements are shown here in this presentation. Smart or intelligent materials are a group of new and state-of-the-art materials now being developed have a significant influence on many of our technologies. The adjective smart implies that these materials are able to sense changes in their environments and then respond to these changes in predetermined manners, traits that are also found in living organisms. For example, one type of smart system is used in helicopters to reduce aerodynamic cockpit noise that is created by the rotating rotor blades. Piezoelectric sensors inserted into the blades monitor blade stresses and deformations. Feedback signals from these sensors are fed into the computer-controlled adaptive device, which generates noise-canceling anti-noise. Until very recent times, the general procedure utilized by scientists to understand the chemistry and physics of materials has been to begin by studying the large and complex structures, and then to investigate the fundamental building blocks of these structures that are smaller and simpler. This approach is sometimes termed top-down science. However, with the advent of scanning probe microscopes, which permits observations of individual atoms and molecules, it has become possible to manipulate and move atoms and molecules to form new structures and thus design new materials that are built from simple atomic level constituents. This ability to arrange atoms provides opportunities to develop mechanical, electrical, magnetic, and other properties that are not otherwise possible. We call this the bottom-up approach, and the study of the properties of this material is termed nanotechnology. The nano prefix denotes that the dimension of these structural entities are on the other order of a nanometer. Now that we understand the different advanced materials, we are now ready to discuss the modern material needs. The modern material needs are sophisticated materials that are sensitive to the environment and climate change. Also, nuclear revolution need materials to avoid radiation exposure. Nuclear power produces infinitely large amount of energy that can fuel the future. Transportation needs materials for weight reduction and increased efficiency. Solar technology needs cheaper and efficient material to harvest solar energy. Metal extraction method needs material to reduce the amount of energy used. And finally, materials that are needed for space exploration. We are now on the last part, which is the chemical composition of engineering materials. Grinding is an abrasive machining process that causes grinding wheel as the cutting tool. Silicon carbide, exceedingly hard, synthetically produced crystalline compound of silicon and carbon. Its chemical formula is silicon carbide. So in this grinding abrasive machining process, the chemical composition of the grinder is silicon and carbon. Silicon is hard, brittle crystalline solid with a blue-gray metallic luster and is a tetravalent metalloid and semiconductor. Carbon, on the other hand, is a non-metallic chemical element which makes up only about 0.025% of the Earth's crust. Silicon and carbon are both nonmetals. What kind of bonding exists between nonmetals? So the correct answer is covalent bonding. A covalent bonding is when a stable electron configuration is created by sharing of electrons between neighboring atoms. Two atoms that are covalently bonded will share at least one electron from each other. Covalent bonds can be very stiff and generally give a material with very high elastic modulus, high strength, high melting point, and low electrical conductivity. Thus, as you can see in the example, the grinding process, we use a material that has a covalent bonds. Covalent bonding is the dominant bonding found in silicate ceramics and glasses. It also occurs in the backbone of polymer chains and in the crosslinks in thermosetting polymers. We have here another example. Spark plug, which is a device for delivering electric current from an ignition system to the combustion chamber of a spark ignition engine to ignite the compressed air. The electrodes in a spark plug typically consist of high nickel alloys, while the insulator is generally made of aluminum oxide ceramic, and the shell is made of steel wire. The chemical composition of our aluminum oxide ceramic part is the aluminum and oxygen. Aluminum is the most abundant metallic element in the Earth's crust and the most widely used non-ferrous metal. Oxygen, on the other hand, is the chemical element which is a member of the chalcogen group in the periodic table, a highly reactive nonmetal and an oxidizing agent that readily forms oxides with most elements as well as with other compounds. Aluminum is metal, while oxygen is nonmetal. What kind of bonding exists between metal and nonmetal? The correct answer is ionic band. It is formed between two elements when one has a smaller number of electrons in the valence shell, which is the metal, and one has an almost full outer shell, which is the nonmetal. Atoms are more likely to accept electrons if they have an almost full outer shell, which is the elements on the right side of the periodic table. Ionic bands are strong and stiff. As a result, they generally give a material with high strength, high elastic modulus, high melting point, and poor electrical conductivity. Then we have here another example. Nearly all vehicles on the road today are made of steel because it is the easiest and best material for designing safe vehicles. The chemical composition of steel are iron and carbon. Iron is by mass the most common element on Earth, right in front of oxygen, forming much of Earth's outer and inner core. Both iron and carbon are metals. What kind of bonding exists between two metals? The correct answer is metallic band. The electrons are surrendered to a common pool and become shared by all the atoms in the solid metal in a metallic band. Metallic bonding generally results in a material being strong and stiff and gives high elastic modulus, high strength, good electrical conductivity, metallic luster, and high ductility. In summary, we were able to discuss the historical perspective of the development of engineering materials, the difference between material science and materials engineering, the reason why we study material science and engineering. We also classified the materials into different families and also discussed the different advanced materials and the modern material needs. Finally, I gave you some example on the chemical compositions of the different engineering materials and the resulting properties or characteristics as a result of this chemical composition.